Hello and welcome to today's webinar. My name is Fauzi Walgin. I support the product development in the area of interfaces. I will be the presenter today. Sandy Matula will answer your questions in the chat. She is responsible for the customer support at Luval. And the topic for today is RFM6 and Grasshopper interface, the connection between modeling and design. For questions, you can press the question button with the question mark and then enter your question down here. You can also contact us via email if you have questions afterwards. Okay, the content for today, as always, at first a preview to the future development. Due to the Christmas period, the release of the new functions are delayed and the implementation will take place after this webinar. So that's why we are presenting the new functions, not the new functions today, but giving a brief overlook on functions that will be added in the near future. Afterwards, we give you an overview about the geometry in Grasshopper and how you can connect the geometry to the Bluebell components. And at the end, I show you how you can control the calculation and results documentation with Grasshopper inside RFM6. Okay, let's start with the upcoming functions for the Grasshopper interface. At first, we will add a new component for design supports and a deflection analysis for timber design. Also a new component for member supports. And we also extend the member eccentricity component with the possibility to define relative member eccentricities for members. And also we will have the possibility to define the node type on member. As well, we also extend the existing surface temperature load with inputs for linear temperature load and also extend the component with the load type axial strain. Yeah, and that's just a small overview with new upcoming functions for the Grasshopper interface. If you want to see all the new features of the Grasshopper interface, you can go into extranet on our website and there you find the documentation for every new function with the upcoming update. Okay, so let's start with the structure. Structure for today. Let me first show you a picture. So the inspiration for today's structure is this tower model. It's the tower model in the Vaublais. It's a tower structure in Switzerland, in the area of Lausanne. I hope it's the right how I pronounce it, in Lausanne, yeah. And it's like a cone-shaped tower with two independent staircases. So we have a spiral stair up here. It's like helix shaped and it's generated like step beams that are stacked on top of each other, and these step beams are held together with a metal rod in the middle and with the edge beam on the side. So, and that's how now I show you how we organize the script for this model. Let me look. Okay, I divided the model in three parts. We have a bottom part for the first spiral staircase, for the second spiral staircase, and the third spiral staircase. Every staircase has a different angle for the steps. So we have, here you can see we have the part 1, the first level of the structure is here, the part 2, the second staircase, the second level of the structure, and the third part, and also the roof and the observation platform at the top. Okay, and following idea behind this, imagine we are in the early phase of our concept finding phase, and we want to consider different variants or different alternatives for our structure. And as a part of this consideration, we limit our structure changes with help of parameters we have defined in the script. So we can, for our structure, for example, adjust the radius at the top. We can adjust the radius at the bottom as we wish. And we set again 6. And we can adjust the number of columns we want for this model. And also we can adjust the height for every part. So we have the height for part 1. We can adjust here. Also for the second part, we can also adjust the height if we want. And all these heights are connected in this one number slider. So we now can adjust the height for the row structure. And it's like adding one step always to every part of the structure. So we have a height step of 0.2 meters. It always stays the same because it's like this beams stacked over each other. And we can now control this model by adding always one step to every part of the model with this parameter. So we adding steps to the model, and also the spiral angel always get bigger if we add more steps for every part. Okay, and now we don't just want to look at the aesthetics and the design of the structure, we also want to read out the structural engineering results for possible design variants, for example, without much effort, and include our results into this concept finding process. Yeah, and that's the whole idea behind this structure. So we need to connect this parametric geometry to a working parametric analytical model, and also extract the results or calculate the results for this model instantly. Yeah, that's the plan for today. A small brief comment on the geometry of this model. Let's make it. No, we need the model to look at, but we can make it smaller. So let's have a look at this structure of the geometry. At first we have, here you can see the lines for the steps. It's our steps going upwards. And these steps have an intersection with this edge beam. These are the intersection points with the edge beams. And this edge beam also have an intersection point with the columns. So if we generate or interpolate this edge beam only with the nodes of the steps, we get the correct line, but we don't have the intersection point with our columns. And we need these intersection points later for member set definition, because we want to define member sets for our columns. So how I solved this, I took the intersection points with the edge beams with the columns, and the intersection points with the edge beams with the steps. These are these points. You can see both points. Now I generated a line for our edge beams through these points. The problem we might get here is if we adjust our parametric model in some cases. For example, if we move the number of columns we have here, and in some part we get double points. For example, let's have a look. So example here we have the same intersection point for the column and the same intersection point for the stair beam. So in this case we would get double nodes in RFEM, and to avoid this you can use this Cal duplicates component under vector. It's remove double points, and you can just leave one or cull all. It's how you want it. Now here we have 2 points at the same spot, so we can just leave 1 point of them and don't get double nodes inside RFEM afterwards. And afterwards we can also divide this, it's one polyline curve we have here, into structure, and we can divide it in segments, divide into segments with the shatter component. So we have, how would say, we can divide line into segments, so we are able to assign for every segment their own index number in RFEM. Afterwards it's copied on the other side. It's like used this mirror function to copy it for the other staircase. And this is how all this script working for all the parts. It's always the same concept. I don't show you more about this geometry. You can have a look at it for yourself afterwards. So what's also important for us is that we also divide the columns. Like I said, we have here the columns lines and we want them divided at the intersections. Why do we need this? We want to design the columns afterwards as a set of member, and we need this intermediate nodes to define lateral supports at the intersection points. So herefore I used this line intersection component, so I can define a line I want to intersect, that's our columns, and I can define line this column is intersecting with. So column intersecting with this edge beams, and now I can get the segments for every column on a separate branch. So here can you see I only get line segments out of this component and have all segments stick together in one branch for every column. This we can also later use for our member set definition in Grasshopper. Let's make it very easy to define afterwards. Okay, that's just some comments on the geometry. If we look at the script we have now for rule geometry, we have the lines for our stairs, we have the lines for our columns, we have the edge beams. For our structure we have the observation lines for the observation platform, we have the roof beams, we have the vertical stands outside, and also the rod in the middle. So now we want to connect these simple lines to our RFEM plugin and use it for calculation. Let's start at the top. Here you see the RFEM components. Let's start at the top. It's the same procedure like in RFEM. At first we define the material, then the cross sections, and then we assign member to the Grasshopper lines we have here. We assign the member. So let's start at the top with the material. I'll make this big. First step is to assign an index number. In RFEM you have an index number for every object we define. So you have the index number for materials, you have the index number for sections, for nodes, for lines, etc. So that's the same workflow for the Grasshopper components. In our Global plugin after installation, you have load elements and model data elements. Here you find the material component. You can define some different stuff we don't need today. So first we can define a material number 1 and the material name. Here's something I like to mention. Where you get the material name, we don't have a component for the whole material library from RFEM, because it would be a very big library for every country. So it's very easy to define its own little library as a component. So how do you get the names of materials and also for sections? I will show you this in very quick in RFEM. Maybe take this. All we need are the names of the sections, for example, and also the names of the materials. Here you see the full names. It's very important that you use the full names. Where you get the full names from. If you open the options, the program options, you have here the display settings to show full section description or show full material description. That's important because RFEM use the name of the sections, for example, and also the code it's designed with. And if we don't display the full name, you will get only these names, and this then we use a complete different standard you don't want to have. So make sure you always have this option activated to display the full names. And here you also get the standard you're working with. So afterwards we can copy these names and generate a value list, a simple component in Grasshopper, and inside this value list we can edit it and insert these names. So these names will insert in this value list. So now you have a small component with your own library, and you don't have to do it every time. You can save this component as a user object. For example, you can here create a user object for this component. Here you can set some values name, RFEM sections, for example, add a description to this and select in which category you want to have it. Select an icon and add it to your Grasshopper interface. I already did this. I'm using here some components for my RFEM materials. We have materials defined, and also component for the sections. We have sections defined and can always use them in every project. So, and there's maybe some other important hint. If you use parametric sections in RFEM, so if you define something like this section, you have iris parameters you can define in millimeters. It's a bit tricky in Grasshopper because Grasshopper always expect SI units. So our interface works with Web Services API, and this always expect SI units for the export and for the export. And for this, I generated some tools for myself. Maybe I can show this export cluster. Maybe for the basic rectangle section, I always can define the height, define the values I want for my section, and then I can just copy this name and insert it into my list. This is automatically generated from Grasshopper, so you don't have to find. You can also you can just insert the name Press OK, and you have the section now inside your little library. Here you need to make sure if you add some sections while working that you need to save this component again, so you can just delete this user object, mark it and say okay, save this user object. This will be taken over like you defined already. Press OK, and this section will be added to this library. Now let's have a look to the further components. Give me a minute. Yeah, to the section component. It's also the same. You define the section number, define the section name again with your little library you created, and the material number. The material number can be taken over from the material component. So if you adjust here the number will also be adjusted here. We have different inputs for section, rotation, angle, and some other inputs we don't need here now. And now let's connect the first Grasshopper lines to RFEM with creating the member component. So here we have some lines from our stairs. Maybe I show it like here. Yeah, lines from our stairs. And here I have maybe also a hint from my side. I had some problems with double lines. Because as I generated the stairs, I got the last stair of the line is also the first line of the platform here. So I get always double lines at these areas. It's more like an unclean modeling from my side. But for this problems, there's a easy solution with this component. It's from Kangaroo. Remove unique line components. Notice you can just remove duplicated lines and don't have to remove them with lists or something else. So here you have 328 values, 328 lines, and here as the output you have 320 lines, so 8 lines removed, 2 lines, 4 lines for every platform. I have doubled lines. Okay, the next step would be section distribution. This is controlled by value list, where you can assign what you want. If you want a uniform member, if you want a linear member. Yeah, I think that's the parts we support for now. So it's basically always uniform if you don't define anything. So you don't have to define this if you don't want something specific. The next step is to connect the section. So our sections are already defined, so we can just connect this component for our member. And afterwards we have, I forgot something, we have the member number. The numbering is assigned automatically, but for load definition in Grasshopper, it makes sense to define it by yourself. So we want to start the numbering by 1. It's very easy. You can use this series component, and we start the numbering by 1. I have a step of 1, and the count is our value of lines for the stairs. So we take the lines from our stairs, it's the line number, and this should be our list length. And this list length can be used as a count for our list. So we have now here number 1 to 320, and we just connect this to the member number input, and we will generate in RFEM members with the index 1 to 320. Now if we generate other member components in Grasshopper, we don't want to start the numbering with 1 again. We want to continue this series. This is also really easy done. You can just read out the last number from this component, it's 320. Here we read out the last component, last number of this series, add 1 to the series, and now we have the series starting with 321. Step also 1, and the count again the next list forward. It's our column list. Yeah, and we have now the series for our column members. And this just, if you can generate further members, like here, it's just a copy and paste function. So you continue this series, this component, and here the numbering is continued with this series. Here it ends at 441, and this starts at 432, and so on. So it's very easy to find for numbering. Next step would be to define maybe some hinges for our structure. Here we can also define hinges inside Grasshopper. So for example, we want to define a hinge at the end of every step, and we are not sure if it's the hinge start or the hinge end of our member, and this can be easily checked inside Grasshopper. So for this I also generated a little help tool. For me it's just, let's have a look, just a component where you define or evaluate a point in the middle of every line, and then you show the vector of every line. And this line start and line end also transferred to the members in RFEM. So example, for the stairs, we don't know where's the start and where's the end for the lines. We can check it really quick. So okay, you see the arrow in this direction. So we have here the member start and here the member end. And we want to define here member hinge. We need to define the hinge at the end of the member. So just as a small tip that you can always check where the start and the end of the beams will be afterwards in RFEM. Okay, something else. No, we don't find anything else here. Next step would be, I want you to show the, look at the time, the member sets. These are member sets for our columns. So we have here our column lines. And again, why we want to use member sets. We use member sets because we can afterwards define lateral supports. Yeah, we can afterwards define lateral supports at the intersection points or the intermediate nodes of every column. And that's why we define here the member sets, and how it's done. First we need the numbering. It's again easy done, and afterwards we need a member number as input. Here we have our members for the columns we want to use. So here see our columns, and here we have all members from the columns. And here we have a member input, not a Grasshopper line input. So we have now all members in one component, and if we connect these members to this component, we will get one member set and have only one member set with all members inside. But we do not want all members in one set. We want a one set for every column. So that's why we can use the structure of our lines division that I showed you here. Here we already have every line segment from one column in one branch. And we can copy or use this branch structure also for our members. Yeah, so we have all the segments of the columns in one branch in this tree structure, and our aim is to organize our members also like this line segments. And how it is done. And we have, let me show you real quick. We have some component, the destruct path component. With this we can connect this component to our line segments, and to copy this let me check, to copy this branch structure, and afterwards we can take our members, put it inside this unflattened tree component, and say, okay, organize these members from this with this branch structure from our line intersection segments. Afterwards we can just trim the tree, and we get the same structure also for our members. And this now we can use for a set of members. So here you see we have 70 members, 70 lines, it's 18, 24. Let me show you real quick. We have here 24 member sets, and every member set is connected to one column or to all members from the correct column. And so that's the easy way to generate member sets in Grasshopper. What's the next step? If we want to design the columns with the member sets, we need also to define some design properties for these member sets. And how is it done? Here we have some design property options also available for the members, but we won't only look at the member sets today. So you can activate design property sets here, like it's done in RFEM. And now we can assign only numbers. So what are these numbers? Where we get this number from, it's a part of a workflow I will show you right now. So let me show you how it's done and why it's only numbers, because we can access a template in RFEM with Grasshopper, so that we can only adjust numbers for the design properties. So what's a template in RFEM? Let me show you quick. And if you are in RFEM file, you have always the possibility to save a file as a template. So if you create a new file, you have the basic inputs like here name and so on, and here you have also the possibility to start the new model with a template. Template is like a predefined file where you have objects and settings defined. For example, you can activate Timber Design, you can select your basic standards you like to calculate. You can already define load cases, you can define load combinations. You can also adjust the result tables you want to shown afterwards in the printout export or in the Excel export. And you can also, what I would like you to show, define design properties, for example, timber design properties or types of timber design. So for example, here the effective lengths are defined with types. We have here number 1, number 2, and here you can define inside what you want to look at. So we in Grasshopper, we only refer to these numbers from this defined template. So here I have template where effective length index number 1, we have defined intermediate nodes for our structure. Define service classes 1, 2, 3. I can assign 2 in Grasshopper, and you can also define for the Timber design, for example, the ultimate configuration. Like you want the configuration with stability design and one without stability design. Okay, need to uncheck this. It's wrong defined. Yeah, one for the stability design and one without stability design. And afterwards, if we define everything inside RFEM, we can also, I forgot one thing, we can also define some settings for our printout report. For example, here you can define what you like to see in this report. I get here some settings, and afterwards you can save this also as a template for use afterwards. It's the same with if you print out graphics in the report. Here you can print out graphics in the report. You have the settings to set more than one print in the report, and you can define which view you want to see in reports. You can create a view in every direction. You can create views for load cases, for results, for the design, and so on. This also can be saved inside this template, save as template. And if you have all this definition, you save this file as template. It will be saved as template. An important thing, this template file is generated as FT6 file. And to access this file, you have to connect your project at the folder you saved the file inside to your Loomer project. So if you open the Loomer Center, you have here the tab model templates, and inside here you can just connect folder as a project. For me, it's inside my download folder where I already have some templates defined to use. Okay. So let's have a look back into Grasshopper. So we have defined our design properties in this template, and now we only refer to the numbers, index number of the definitions. So we have here something for steel design, aluminum design, and we use now the timber design, the effective length, the service class, the ULS settings. And how, yeah, okay, that's, I wanted to show you now. Give me a second. What should be next? So yeah, and that's why we use templates at first. And what's else the benefit of using these templates? This also allows us to control or define loads very quickly, so we don't need to define like load cases and load case combinations inside Grasshopper. You have the possibility to define it inside Grasshopper, but if you always already defined this in your template in RFEM, you can just refer to this template and don't need to define these components by yourself. For example, just for a quick show off, here we have some surface load. What's the load input? We have surface load number. It's automatically generated, or you can give it a 1 if you like, and here just a load case. So you don't have to define this load case component fully and connect load case number here. You can just refer to the load case in our project, load case number 2. It's already defined in this template. So it's regenerate the load in this load case. At the other inputs, you already saw, I think. It's always controlled with value lists. And here I also have a member load for other load case. You just define the member component, define everything with value list, and assign the load case number. And that's all, just connected to the RFEM component, export component afterwards. Let me show you now the RFM export component. So I have defined my member inside here and collect it in this data component, so I don't have to connect everything with my RFM component if I make some changes. Here we have the export component. It's under RFM6 main tab. Here we have the export. Here the export component. First, you can define here Boolean toggle to run the export. If you activate it, the export is running. For the input, you connect all the global components we use. It's easy to check if you click the component, press Ctrl and left arrow button, you see which components are connected. Now it's directly connected to materials, and if I look, okay, every RFM component is green, they're all connected to our component. What else we have to define? We can flip the axis and some other settings, but the most important for us now is the use of the template. So we saved our definition inside here as a template, and this template is located in our downloads folder. Here again we can copy this template, the path of this template, and insert it inside RFM. So we have the template path inside here we refer to, and we give a model name to our structure. Most important thing, you have the override function on false, because what's happened if we export the structure now to RFM, it will generate a new file. This file will get his name, and we will load a template. That's our templates from the downloads folder. It will load a template, and afterwards, if we set this on true, it will override our model, and it will override all definitions inside this template. So it will not work with the override function. So what's most important to set it on false. And afterwards, if we export as a structure, we also want to calculate if it's exported successfully. So for this we can use our, where is it? Here. We can use our calculation component to start the calculation in RFM. And after the calculation is successful, we can also use this export printout report component to export the printout. We define a path where we want to save this printout, and all settings for the printout will be used from this template we defined. Okay, this is also for the Excel export. If we define, let me show you the results table inside a template file. Don't check everything, for example. This will also only export the result tables we want to see in this CSV files. Okay, now I want to show you how it looking if you export now the structure. Let me close this one. This one we also don't need anymore. So we have our structure, we have our RFM components all connected. Now we can start. Let me make it half screen. What's that? Okay. We can't start the export. If we set the run boolean to true, the export will be started. Here is the connection to RFM. It's logged the application. The template is loaded. You see already load combinations inside this file. Take some time. Okay, the structure is there. Now you see the application is logged again. It's generating the mesh and calculating the static analysis. It's calculating now the timber design we defined with the design properties already in the template, and afterwards it exports everything in printout report. Now you see this is green, it's successful, this is green, it's successful, and report also exported. Now what's the result? Now we have a small generated report with every important infos we like to see. For example, the load cases inside here, the part list, a summary of the deformation, the support forces later for the ground, for the foundation. For example, let me see, and static analysis results as a summary, the member internal forces, the total maximum and minimum forces we have in this structure, and some overview for the timber design. Here we have to look at the sections again and adjust them. And here we have our member sets, that's our columns 1 to 24. And now you have a section proof and stability proof for every section as a small overview, and also the views of the model, so you can quickly check if it's okay for you or not. So now if we adjust this parameters and export it again, we can generate other reports very quick for the structure. Why it's not showing? Yeah, and you can look at different parameters and how it's affect your structural analysis in some point. I have a quick overview for every tower you calculate, maybe something like this. You have a quick preview, a quick pre-design with settings you adjusted. The tower maybe looks not so good, but just as an example. Yeah, and this is how you can create different reports and have some significant information inside from this analysis inside Airframe. So this is not a full calculated structure for sure. It's more like a foundation for discussion of alternative designs of a structure, and so you can adapt the parametric geometry, for example here, and get adapt the parametric geometry and get instant results for estimate structural engineering results, or for the variation of your structure directly. Of course, I'm missing out looking at different analysis points for a tower like this, for like the dynamic analysis, the structural stability, but this should be served more like an idea of how you can use our interface, or how it can be used to or how you can interact between Grasshopper and Airframe in the documentation. And thinking one step ahead, maybe you can automate this design process. And now we have a different now we have a large number of different configurations for the structure. We have our parameters, we have many possible solutions for a structure depending on the defined limits of these parameters and depending on the goal we aim at. But maybe at some point we have an optimal solution with the optimal parameter settings inside here. And this for the future, sure, our aim to optimize the process to read out results into Grasshopper and optimize the structure based on these results we read out of Airframe. But that's a different topic. The aim for today was to show you the first steps of linking the parametric design with the structural design And yes, that's all for today. I thank you for your attention. I hope you can benefit from somehow from this webinar for your own project, and wish you a nice rest of the day. Goodbye.